When people think about military technology, they usually imagine finished equipment: aircraft, ships, vehicles, weapon systems, radar, or communications gear. What they rarely see is that military technology in the UK is not defined by individual machines. It is defined by systems that design, build, certify, maintain, upgrade, and supply capability over decades. Most military technology is never truly finished. It is continuously adapted, repaired, modified, audited, and supported. This explanation describes how military technology is built, maintained, and supplied in the UK, focusing on the digital systems, industrial processes, and organizational coordination that make this possible. It is not about tactics or battlefield use. It is about how complex technology is turned into dependable capability at national scale. Military technology in the UK begins long before anything is manufactured. It begins with capability definition. Defense planners define what a system must achieve, not how it must be built. For example, a requirement may specify detection range, reliability, interoperability, and life cycle duration, rather than a specific design. These requirements are modeled digitally. Simulations explore performance under different conditions. Trade-offs are tested. Cost, risk, and time are assessed. At this stage, military technology exists entirely as data. Design work then begins. UK defence industry uses advanced digital engineering tools, computer-aided design, digital twins, systems engineering platforms. These tools allow entire platforms to be assembled virtually before physical components exist. For example, aircraft systems are integrated digitally to test how avionics, software, sensors, and power systems interact. Problems discovered here are far cheaper to fix than problems discovered after manufacturing. Once designs mature, manufacturing begins. Military manufacturing in the UK is highly specialized. Many components are produced in small quantities. Tolerances are tight. Quality assurance is extensive. Every component is tracked. Serial numbers, batch records, material provenance. This tracking is digital. It ensures traceability throughout the system's life. Supply chains are complex. A single platform may involve thousands of suppliers. Some provide physical parts. Others provide software. Others provide testing or certification. Supply chain management is therefore a major technology challenge. Digital systems track supplier capacity, lead times, dependencies, and risk. Disruption at a single supplier can delay an entire program. Identifying that risk early depends on data visibility. Once equipment enters service, maintenance becomes the dominant activity. Military technology spends far more time being maintained than being built. Maintenance is planned digitally. Service schedules, usage tracking, condition monitoring. For example, modern aircraft engines generate continuous performance data. This data is analyzed to predict failures before they occur. Maintenance is scheduled proactively. This improves availability and safety. Configuration management is critical. No two platforms remain identical over time. Upgrades are applied. Repairs differ. Software versions change. Digital configuration systems track exactly what is installed on each asset. Without this, safe operation would be impossible. Software now defines much of military capability. Radar performance, communication security, electronic warfare, all depend on software. Software updates are treated as engineering changes. They are tested, certified, rolled out gradually. This process mirrors safety-critical industries rather than consumer technology. Supply does not end with initial delivery. Sustainment contracts often last decades. Spare parts must remain available long after production ends. This creates challenges. Suppliers exit markets. Components become obsolete. Technology evolves. UK defence industry uses obsolescence management systems to track at-risk parts. Alternatives are qualified. Redesigns are planned. This work is largely invisible but essential. Logistics is another core system. Military supply chains must function globally. Parts must reach deployed forces. Conditions may be hostile. Infrastructure limited. Logistics planning uses digital tools to model routes, storage, demand, and risk. Stock levels are optimized. Overstock wastes money. Understock reduces readiness. Balancing this is a continuous data problem. Security runs through the entire system. Military technology supply chains are targets. Industrial espionage, cyber intrusion, counterfeit components. Digital security controls protect designs, data, and production systems. Suppliers must meet security standards. Access is controlled. Activity is monitored. A compromised supplier can compromise the whole system. Certification and assurance are fundamental. Military technology must meet strict safety and performance standards. Testing is extensive. Laboratory testing, environmental testing, operational trials. Results are recorded digitally. Evidence is retained for decades. This allows decisions to be justified long after personnel have changed. Upgrades illustrate how systems evolve. Rather than replacing platforms frequently, the UK upgrades existing systems. Sensors are replaced, software enhanced, communications updated. This approach reduces cost and preserves operational familiarity. Digital integration is key. New components must work with old ones. Testing focuses on interaction, not just function. Industry and the military operate in partnership. Industry builds and supports. The military operates and provides feedback. Data flows both ways. Operational data informs design improvements. Design changes improve maintainability. This feedback loop is central to long-term capability. During crises, supply systems are stressed. Demand spikes. Lead times shorten. Logistics becomes critical. Digital visibility allows prioritization. Critical units are supported first. Less urgent activity is delayed. Without data, this would be guesswork. Defense technology also relies on skills. Engineers, technicians, software specialists, supply chains include people. Training pipelines are long. Knowledge is perishable. Digital documentation preserves expertise, procedures, design rationales, maintenance history. This allows continuity across generations. Military technology in the UK is therefore not defined by factories alone. It is defined by interconnected digital systems that manage complexity, risk, safety, and time. Build is only the beginning. Maintenance sustains capability. Supply enables operations. Together they form a technology ecosystem designed to endure for decades under uncertainty. This is how military technology is built, maintained, and supplied in the UK. One concrete case study helps show how all of these systems interact over time. Consider a long-serving military aircraft platform operated by the UK. The airframe may remain in service for several decades. During that time, almost every subsystem changes. Avionics are upgraded to remain compatible with airspace regulations and allied systems. Mission software is rewritten repeatedly as threats evolve. Communication systems are replaced to meet new security standards. Sensors are refreshed to improve accuracy and reliability. None of these changes happen in isolation. Each modification must be digitally modeled against the existing configuration of the aircraft. Engineers assess power, cooling, weight, and electromagnetic compatibility. Software changes are tested against both new and legacy hardware. Safety cases are updated to reflect altered behavior. Certification evidence is regenerated and reviewed. At the same time, the supply chain must adapt. Original component manufacturers may no longer exist. Electronic parts may be obsolete. New suppliers must be qualified. Equivalent parts must be tested and approved. Digital obsolescence tracking systems identify these risks years in advance. Maintenance data from operational use feeds back into planning. If a component shows unexpected wear, inspection intervals are adjusted. If software faults appear under specific conditions, updates are prioritized. Availability targets drive decisions. The goal is not perfection. It is predictable, safe operation. Logistics systems ensure that spares are positioned where aircraft are based. Stock levels are adjusted based on usage patterns. During deployments, supply routes are reviewed continuously. If access changes, alternatives are planned. All of this is coordinated through digital systems shared between the military and industry. No single organization controls the whole process. Capability is sustained through coordination. After many years, a decision may be made to retire the platform. That decision is informed by data, maintenance cost trends, upgrade feasibility, supply chain fragility, replacement readiness. Even retirement is managed digitally. Data is archived. Configuration records are preserved. Lessons are captured for future programs. This case study shows that military technology in the UK is not defined by a moment of delivery. It is defined by decades of controlled change, managed risk, and continuous technical stewardship. Another case study illustrates how military technology is sustained when the platform itself is less visible but just as critical. Consider a secure military communications system used across the UK Armed Forces. Unlike a vehicle or aircraft, this system is largely software-defined. Its physical components may be servers, radios, terminals, and network infrastructure. Its real value lies in encryption, key management, routing, and resilience. This system is never fully static. Threats to communications evolve constantly. Encryption standards age. Attack methods improve. Interoperability requirements change as allies update their own systems. As a result, the system undergoes continuous digital modification. Software updates are planned years in advance. Backward compatibility is carefully managed so older equipment can still operate during transition periods. Key management infrastructure must scale securely while remaining usable in operational environments. Every update passes through controlled test environments. Functional testing confirms performance. Security testing attempts to break the system. Operational trials validate usability under real conditions. Only after this process is the update approved for wider deployment. Supply considerations are different but equally complex. Hardware may be sourced from multiple suppliers. Components must meet security and assurance standards. Firmware is treated as part of the trusted computing base. Any change requires revalidation. Logistics systems ensure that updated equipment and cryptographic material reach units on time. Failure here can degrade capability even if the technology itself is sound. Maintenance focuses on availability and trust. If confidence in secure communications is lost, operational effectiveness collapses. Monitoring systems track performance, faults, and attempted intrusions. Incidents trigger investigation rather than immediate blame. Root causes are identified. Controls are adjusted. Over time, parts of the system may be replaced entirely. Legacy elements are retired. New architectures introduced. This transition is managed gradually to avoid capability gaps. Data from the old system informs the design of the new one. Nothing is discarded casually. This case study shows that some of the most important military technology in the UK is invisible. It exists as software, data, processes, and trust. Building it is only the first step. Maintaining and supplying it securely over decades is the real challenge.